myself Ramyabharathi. I am going to take a seminar on speed control of induction motor. Here we can see the definition of induction motor. An induction motor or asynchronous motor is an AC electric motor which works on the principle of electromagnetic induction. In this motor, the electric current in the rotor needed to produce the torque which is obtained by electromagnetic induction from the magnetic field of the stator winding. Therefore, the induction motor can be made without electrical connections to the rotor. An induction motor's rotor can be either wound type or squirrel cage type. There are two ways of controlling induction motor. One is scalar control and another one is vector control. In scalar control method, the induction motor's speed is controlled by setting the voltage and frequency of the stator so that magnetic field in the gap is maintained at a constant value. To maintain the constant magnetic field in the gap, voltage by frequency ratio must be constant at a different speeds. Vector control. Vector control is also called as field oriented control. It is a variable frequency drive control method. Rotor resistance control. In this speed control method, the rotor circuit resistance is varied by connecting a variable external resistance. This method is applicable only for slip ring induction motor because in squirrel cage induction motor, rotor winding terminals are not available for external connection. Hence, its speed can't be regulated by rotor resistance control. Therefore, this method is not applicable for squirrel cage induction motor. Principle of rotor resistance control. The torque in the induction motor depends on the rotor circuit resistance. Also, the maximum torque in the above figure, the maximum torque is same for rotor resistances R1, R2 and R3, but the slip increases from point A to B and A to C. Maximum torque is same for three resistances and the slip increases from A to B and A to C. This means increasing rotor resistance results in increase in slip. Increase in slip means reduction in the speed of the induction motor. Therefore, we can say that by rotor resistance control, we can achieve variable speed at a constant torque. This is the reason that this method is suitable for constant torque drive. It may also be noted from above torque slip characteristics that starting torque increases with the increase in rotor resistance. Therefore, this method is more helpful when we require high starting torque. Slip power recovery scheme. The basic principle of slip power recovery is to connect an external source of EMF of the slip frequency of the rotor circuit. And the slip energy recovery method provides speed control of a slip ring induction motor below its synchronous speed. A portion of rotor AC power, that is slip power, is converted into DC by the diode bridge. The smoothing reactor is provided to smoothen the rectified current. The output of the rectifier is then connected to the DC terminals of the inverter. The inverter inverts the DC power to the AC power and fed it back to the AC source. The inverter is a controlled rectifier operated in the inversion mode. This method of speed control is used in large power applications where the variation of speed over wide range involves a large amount of slip power. During the speed control of induction motor using rotor resistance control, rotor power is wasted in the external rotor resistance. This rotor power can be utilized to increase the efficiency of the drive. There are two schemes for recovering the wasted power. One is the Scabious drive and another one is the Kramer drive. In Scabious drive, the variable frequency rotor power is converted into DC by a diode bridge rectifier, and then an inverter converts it back to AC and is fed back to the supply main. Thus the slip power is fed back to the source instead of wasting it in the rotor resistance. Static control of rotor resistance. Rotor resistance can also be varied steplessly. The AC output voltage of the rotor is rectified by the diode bridge and fed to a parallel combination of fixed resistance R and semiconductors which realized by transistor T. Effective value of resistance across the terminals A and B is RAB. It is varied by varying duty ratio of transistor TR, which in turn varies rotor circuit resistance. Inductance LD is added to reduce ripple and discontinuity in the DC link current. Rotor current waveform will be shown in the figure after the ripple is neglected. The RMS rotor current will be IR is equal to root 2 by 3 into ID. Resistance between terminals A and B will be 0 when the transistor is on, and it will be R when it is off. After substituting, the equation becomes the power consumed by RAB per phase is power consumed per phase is equal to PAB by 3, 0.5 into R into 1 minus del into IT square. Rotor circuit resistance per phase is increased by 0.5 R into 1 minus del. Thus, the total rotor circuit resistance per phase will now be RR. Slip. The speed of the rotor magnetic field in the induction motor lags slightly behind the synchronous speed of the changing stator magnetic field. The difference in speed between the rotor and the stator fields is called slip, and it is measured in percentage. Slip is equal to ns minus n by ns, where ns is the synchronous speed
and n is the rotor speed.
Per minute, the rated speed is the speed of the rotor. Slip.